Testing. Testing, testing. Testing, testing. Yeah, we're good? Are you sure?
Yeah,
Okay.
positive.
Okay, thanks.
Anything. Usually we hear music for the BOT, so maybe that's what it is. Okay. She's going to talk on that microphone.
Hello, all. It's on. Great. Well, I'm glad to see you all here. I'm Dr. Jake Hartman, and welcome all to our second talk of the Carnegie at PCC series. I'm very much looking forward to it. Thank you. Just a few points. First off, of course, please do silence your phones for the duration if you have not already done that. I want to give a quick thank you to some of our student volunteers who were a great help in getting the word out, hanging posters, and generally directing people to Creveling Building, which it seems that not that many people on campus know where it is. So thank you to the Astronomy Club and Geology Club for helping out with that. And I also want to give an advertisement for the third and final talk of this series this semester. That will be on November 20th, also a Wednesday, same time, same place, 6:30 in Creveling. And that will be Alison Strom, also of Carnegie, who will be talking about the DNA of galaxies. So I encourage you all to come to that third series in our semester of talks. And of course, bring family and friends. Tonight, I am very happy to be welcoming Dr. Rosalie McGurk, who is Carnegie Postdoc of Instrumentation. She's been with Carnegie since about 2017, working on some of the work that she'll be talking about this evening. Before that, she was at the Max Planck Institute in Germany, also doing some instrumentation, and before that, got her PhD at University of California, Santa Cruz, where she studied active galactic nuclei.
Active black holes.
Active black holes, absolutely. The particularly hungry ones that are still eating all of the stuff around them. Maybe we'll hear a little black hole stuff tonight. All right, wonderful. Everyone likes that. And yeah, so I'm particularly excited about this because when we think about astronomy, we typically think about, you know, the facts. We think about the black holes. We think about the planets. We think about the galaxies. But we don't often think about, well, how do we know that? How do we get that information? We're privileged to be in the same town, Pasadena, this awesome astronomy town, as Carnegie, which is building some of the world's largest telescopes, which ultimately answer these questions. And a telescope is not just some giant bucket collecting light raining down from the sky, though that's part of it. And it's not just a bunch of mirrors and possibly lenses that focus that light, though that is part as well. Really at the heart of the telescope is the instrument that interprets that light, that makes sense of that light, and really gives you the data that tells us about those stars, or black holes, or galaxies. And I think that that's probably the hardest part, interpreting all of those photons, all that light that's coming in. So I am very excited to hear about your work on this subject. Thank you again, Dr. Rosalie McGurk.
Thank you so much. Excellent. Thanks, Cenk, for the introduction. Can you guys hear me mostly in the back? Okay, great. And if I start being too loud, do let me know, because I'll get excited while I'm talking about this, and I get louder. It's not a surprise. Anyway, so I'm going to talk about a new tool to map entire galaxies. So what do I mean by that? So first I'll talk about an introduction to spectroscopy. Then I will talk about the different types of spectroscopy, long-slit versus integral field spectroscopy, and I promise to actually define what those mean. Then I'll tell you about my instrument and the science that it will be able to do. So let's jump right in. So you all are here because you're interested in astronomy, and maybe also some other sciences, and I'd like to tell you all the other sciences, at least theoretically, have it easier than astronomers, because a lot of scientists can go out and touch what they're studying, or at least observe it on a reasonable scale. We mostly get light from our sources. So that's good. Nice start, just light. So light's pretty good though, because we can do a lot with it. We've had to make the best of what we can do, to learn as much as we can. So when we're talking about getting the light, we will take that incoming light. I'm gonna wave my hands mostly at this one, unless people think I should point at that one too. We take the incoming light, and then we send it to some type of telescope. And does anyone recognize the silhouette of this one? It's Hubble. Okay, so we got some astronomers. Or people who know silhouettes, one of the two. But the classic telescope is made up of a primary mirror, and I'm going to say this, astronomers are not creative in naming things. It's the primary mirror because it's the first mirror the light hits, not creative. So it hits the primary mirror, it bounces to the secondary mirror because it's the second mirror, the light, yeah. Anyway, so and then it bounces to some sort of instrument that will receive the light and maybe do stuff to it, and then record it. Okay, it was a nice broad idea. One of our favorite things to do with light is to disperse it. White light is made up of all the colors of the visible spectrum, and passing the light through a prism separates it or disperses it into all the colors. And Pink Floyd is really fantastic for letting everyone know exactly this picture. So thank you, Pink Floyd. You all know that's how it works. So you put some sort of dispersive element into the beam, and it will spread the light out into the component colors or wavelengths. I'll probably forget to say colors and use wavelengths for the rest of the talk, because it's a science talk. And nature is already really an expert at dispersing the light into all the colors. Rainbows are everywhere, and the light and water droplets are really good at spreading the light out. But talking about it in a more scientific context, we'll take some source of light. In this case, we'll talk about white light first. We don't want to look at the entire source. We want to look at just a very narrow portion of the light. So we'll put a mask in front of it. In this case, it's sort of a long slit mask. It's a slit. Then we have a dispersing element, in this case, a beautiful prism. And when you put the white light through, you'll get that continuous spectrum out, or a rainbow. And that's useful because, for example, at the core of our star, if we were able to disperse just the light coming from the core, we would get a continuous spectrum. That's awesome. What else can we do? So if you have heated gas and you try to disperse it out, so one type of atomic gas is right there and it's hot, so it's glowing. When you disperse it out, you get bright lines that characterize the gas. And this has a more common form that we see a lot here on Earth. They're neon tubes, so neon signs, which can actually be, you get all the colors by having different types of gas in those tubes. So by heating the gas or running electricity through it, which is the same thing, we can get it to glow a bright color, and then by dispersing that tube, we can get those component lines that make up that glowing light. And to be a little scientific, these are emission lines. Specifically, the gas is hot and glowing, so all of its electrons are pretty darn excited. So if they were going to be on an energy scale, they would be on the high end of the energy scale. A lot like this child who has had far too much sugar. And then, eventually, the gas will cool and it will emit, come on, you're supposed to, there. It will emit a photon and it will release that light at a specific energy. So like this child, now that they've finally spent all of their energy, now the gas is in a lower excited state or the child is asleep. So that's how we get emission lines. You take hot gas and it will emit photons to try to cool down. Similarly, if you take that same gas, but it's cooler now, and you put it in front of a light source, such as a white light source, and you disperse it, you'll see lines again, but they're dark this time. And they're on top of a continuous spectrum from the white light source. So the idea is, if you've got a cool gas in front of something that's hot, the gas might try to grab some photons that it likes. So in this case, you've got electrons that are sort of at a lower energy, and if you can get a photon of the right energy, or the right wavelength, it will jump to and so like a sleeping child, it will grab that photon and jump to a higher energy level, and be higher, more excited. And so that means that if you were just flooding the area with rainbows and one gas was grabbing out certain wavelengths that were its favorite, it'd leave a dark patch, a trough in the line. So that's how you get your absorption lines, because the gas absorbed those particular wavelengths, like this child. Far too much sugar. But a little more specifically, so we talked about the core of the sun having a continuous spectrum. From Earth, we never see that continuous spectrum. What we actually see is an absorbed spectrum. And that's because the sun has cooler outer layers made up of multiple types of gases that are busy absorbing all the wavelengths that it would prefer out of that continuous spectrum. So you get lines missing. And so this is, a small version. This is the much more beautiful version of that. And you can see how many absorption lines there are. There are zillions of them, to use a scientific phrase, with some of them being larger and some of them being fainter. And the reason we get so many lines is each element has a really unique atomic structure, as you've learned in all your science classes. Whether it's carbon with its 6 protons, neutrons, and electrons, or sodium with more than I'm counting right now, they have unique structures, which means they have a unique set of colors that they prefer to absorb light from or emit light in, either way. So carbon, for example, has so many more emission lines than sodium, which only has a few. And it's really, you can think of it as being similar to barcodes. They're unique identifiers to show us what these objects are. And so really, with astronomers, we're always trying to guess what it is out there, because again, all we're getting is light, so you've got to make the best of the light you have. And if you were trying to identify the barcode on the left, you'd get my favorite Honeycrisp apple, whereas on the right, you would get a navel orange. So it's really important to know exactly how the barcodes should be structured, because it very clearly links you to exactly the atomic element that you wanted to be studying. And again, chemists are really used to using the periodic table and learning from all the information that's contained in it. I see it looking a lot more like this. Because if you just look down a column, you can just see the difference between all the lines, because these are the unique identifiers that lead us to learn about what the element is and how much is and how it's moving. So the unique lines here are really important to discover what elements are present in the spectrum. And just to talk about the sun specifically, we've got all these absorption lines. The giant ones come from some really important species, like hydrogen has a red line and a couple blue-greeny lines. Magnesium has these 3 really bright lines right there, and sodium has a characteristic pair of orange lines. So now you know some of the elements that are in the sun's atmosphere. Awesome. Pretty straightforward. And this is a beautiful plot that we like to show, but we really look at it a lot more like a graph where brightness is on the y-axis and the wavelength or color is on the x-axis. And so you've got your hydrogen lines as the deep troughs there, magnesium, sodium doesn't show up as well, but there it is, and another red hydrogen. So I'll probably be showing most of our spectra like this as we keep going forward, because plots are much more easy to actually, measure the depth of the dip and where the center is and how to actually understand how those lines are where exactly they are in the wavelength spectrum. Because the position is critical, as is the depth of the line. So to recap, emission and absorption lines are unique patterns that identify the elements in the gas, because we only get light, so that's what we have to work with. So we've talked about the sun a lot. What about other stars? What do they look like? So the sun's so huge, it's hard to avoid taking a spectrum of it if you look at anything in the day. To actually look at a star, we have to be a little more specific and choosy about the light we want. So you use a telescope to focus the light into your instrument, but there are so many stars in this field. I mean, there's one horribly, shockingly bright star, Vega, but then there are other things around. So just focusing the light's not enough. We need to put a mask in to block it, and the most classical mask is just a long slit, because it's nice to have some information not just of the object you wanted, but along it. That does mean other objects can creep in, but say you blocked most of them out, ish. Slits are pretty narrow. This is comically wide so you can see it. It'd be smaller. And then you disperse the light and save it onto a detector. And so for this star, Vega, when you disperse it, you can see the spectrum has, I've labeled them terribly, but they're hydrogen lines. They're giant hydrogen absorption lines on top of the emission coming from the core of Vega. Okay, so Vega has a huge amount of hydrogen in its atmosphere, kind of on top of everything else, more than you can see. Good. So putting a long slit across the object and dispersing the light is what I call long slit spectroscopy. But dispersing stars is good, but we were promised more. What about other astronomical objects? Saturn is a fun one because it's close enough that you can actually really do this. And normally when we talk about pictures, when I talk about my long slit, I could mask out the entire beautiful picture, but that's really boring. So we generally do this instead. We'll mask out the portion that we're about to see a spectrum of. So when we do that, I've rotated it because it fits better. We'll get this. So if you dispersed all the light going through that green slit, you'll have wavelength information along the x-axis, but you also get information along the slit. So I was saying, normally you're trying to block out background objects. And so in this case, you don't just block out background objects, you're also getting information from the ring, the disk, and the ring on the other side. It really corresponds beautifully. So you also get information along the slit. And I can't emphasize that enough because it means you're getting spatial information as well as the wavelength information that we were originally interested in. And that's really powerful because if you look at the whole spectrum, okay, it's really beautiful, it looks like a rainbow. We really, on detectors, see much more like this. It's been spread out by wavelength. So the wavelength information is there, not in the color of the plot, but in the spread of the plot. And you can see that our detector actually happens to be more sensitive in the red than our eyes could have seen. That's really cool, nice. Definitely that would have defeated the point if we wanted to just measure red light that our eyes can see. But, okay, what about the spatial information? So if we grab the light from the upper ring and plot it as blue, and the light from the disk and plot it as red, we'll get something that looks like this. And there are similarities and differences. So the blue light is the ring, and the red light is the disk. So similarities, we can see these absorption lines that are coming from magnesium and sodium and hydrogen. Those probably sound pretty familiar because I was just talking about them with the sun. And that's because Saturn's not really glowing on its own. We're actually seeing Saturn in reflected sunlight. So therefore, we should see features that we would have seen in the sun. There they are. Excellent. But there are also differences. So not so much in the rings, but in the disk. And so the disk has these giant absorption lines, which are actually methane. And we see them because the light is actually penetrating partway into Saturn's atmosphere and is reflected at some point, but as it's gone in and come out, it's passed through this volume of gas, and light has been absorbed by the methane in the atmosphere. So just with this long-slit observation, we just learned that Saturn's atmosphere has methane in it. That's awesome. Easy. So what about galaxies? What can we do with galaxies? Of course, we're going to put a long slit on it, because that's intrinsically what we're doing right now. And if we plot it, it's a little more complicated looking. So we've got along the slit here, both there and along the y-axis, and then we've got the wavelength along the x-axis, and I've super zoomed in. So all we're seeing are lines from nitrogen, hydrogen, and another nitrogen line, lots of nitrogen. But they look really different than the lines we were talking about before. They're not just straight across. They actually change their wavelength as they go spatially. That's pretty cool. Why do you think that is? The Doppler effect is the reason, and I'll let someone else explain.
The Doppler effect is the apparent change in wavelength of a wave depending on the motion of the source toward or away from an observer. Astronomers observe this effect with wavelengths of light, but we experience it with sound as well.
If you've ever stood there on a street corner and you've heard an ambulance go by, the first thing you hear is a very high-pitched noise, as it's, say, coming from your left and passing by you. And as it passes by you, what you hear are lower frequencies, a very low-pitched sound. So what is happening in that instance is, as the ambulance is coming toward you, the sound waves that are getting transmitted by the horn on the ambulance, the sound waves are compressed. As it goes away from you, those sound fronts, if you could say, get stretched out. So it corresponds to a longer wavelength and a lower pitch. So you hear a lower sound. The same principle can be applied to light. If you have something coming towards you, you will see it, the spectrum get shifted, but towards shorter wavelengths, and those shorter wavelengths are mainly blue wavelengths. So it gets shifted, they say, toward the blue. If something, and this happens often in astronomy, if something is going away from you, it's going to get shifted toward longer wavelengths, and that's mostly toward the red.
These shifts are classified by the direction they move within the spectrum. Objects moving away from us exhibit shifts to the longer wavelengths. We call them redshifts. Objects moving toward us exhibit shifts to the shorter wavelengths and are called blue shifts.
I told you we weren't creative about naming things, right? Like really fundamentally not creative. So this is a really good, more scientific explanation. This is my favorite video that I'm going to show you, so bear with me, it's silly.
Blue light has shorter wavelengths than red light. When an object in space moves towards us, its light waves are compressed into higher frequencies or shorter wavelengths, and hence we say that the light is blue shifted. When an object moves away from us, its light waves are stretched into lower frequencies or longer wavelengths, and we say that the light is red shifted.
So silliness of cow abductions aside, so specifically we're talking about the Doppler effect, meaning that if you are looking at an object that's moving away from you, the light looks like the wavelengths are stretched, so you see it red shifted, whereas if you're watching the light source move towards you, you're seeing the light blue shifted. Okay, you've got it. Here it is one more time, I'm so sorry. But this is a little closer to what we'd be thinking about in astronomy. Not light bulbs, but some sort of point source moving. So, but our galaxy had something different. It had lines on both sides. This cat is going to help us explore rotation. really specifically. So the left side of the cat is pretty much always coming towards us, like that. And so it's blue shifted, and the right side of the cat's moving away from us, so it's red shifted. But seriously, so the galaxy is spinning. So the left side of the galaxy is being blue shifted, so the light's more blue when it has lines. And so that's how it will look. It will be a more blue line. The center of the galaxy sort of looks like it's towards the center of the possibilities. And then the right side of the galaxy is moving away from us as the galaxy rotates. So it shows that the line is redshifted. So going back to what we actually started this silly digression with, the top side of the galaxy is showing this really clear red shifting of all of the lines. So it's moving towards red wavelengths, meaning the top side of the galaxy is moving away from us. And the bottom side of the galaxy is blue shifted, so it is moving towards us. So that means the galaxy is spinning like this into the plane of the sky. And we just learned that by looking at only the light. So that's pretty awesome because that's so far away. So these long-slit spectroscopy is really powerful. It can reveal the lines, their structure, their motion, but I'm going to now try to convince you that it is inferior because you are missing the big scale structure that you could have seen otherwise. I know, she just keeps changing her mind about what she wants to convince you of. So if you put long slits across these, that's good. You got the big picture, well, the tiny picture actually, you got the tiny picture along the slice. But for this galaxy down here, the Andromeda Galaxy, if you wanted to look at the entire galaxy, you just spent an hour doing that one slit. So now, you have to add another slit, spend another hour, then you add another one, it's another hour. So by the time you wanted to cover the whole galaxy, you just spent at least a night, if not more than a night, trying to cover it. And then, horribly, you have to sew the image back together. So you better be really sure about how you positioned everything, especially if you're coming back the next night. Yay! Our jobs aren't complicated at all. Saturn is, the same way if you were trying to do it. You would want to space everything out if you were trying to learn about, the different composition of the disk, not just of one slice of it, but, weirdly, planets change in composition as you go around. So shoot, you better look at the whole thing, but only with a lot of telescope time. So it quickly gets really expensive and really difficult to try to rebuild the bigger picture. So now you guys are going to have to help me rebuild the picture of a couple of classical, well, one of them's a classical painting and one of them is not. So this one's a classical painting. From these 4 slits, the only light I'm giving you, what's this painting? You guys know too much, okay. So it's Van Gogh's Starry Night, so maybe you'd be good astronomers because you can interpolate from what I just gave you. So, as you got it, Van Gogh's Starry Night. This one will be harder. It's a movie poster. It's even red-shifted and blue-shifted, guys. It came out a couple years ago. Oh, you did it! Yay! So, the point is, trying to reconstruct the bigger picture from tiny bits of information is really hard. There's a classic parable, I think it's Chinese. Depending on what tiny part of an animal you look at, you might come up with a really different picture of what the animal looks like. So if you were looking at it blindfolded and you didn't have an idea of what you were studying, you'd come up with really different ideas of what the animal was. Whether an elephant is a spear, the elephant's a fan or a wall or a rope or a tree. You can see why they'd come to that conclusion, but you missed it. It's a whole huge animal, but it has really different parts. So I think I've convinced you getting the big picture is really important because otherwise it's really hard to learn about. But the problem is if you just dispersed the entire galaxy, just like you didn't put a mask on it, if you look at this picture, you can probably see that bits of the orange light are on top of the bits of green light or on top of the blue light, and it's a horrible mess because you just lost any difference between the spatial information and the spectral information or the wavelength information. So that was a disaster. That is not the way to get the bigger picture. So to sort of wrap that section up, long-slit spectroscopy gives you a really narrow window into the presence of elements and their movement, and it misses the bigger picture. But luckily I'm building an instrument that will give us the entire picture. And so that was long-slit spectroscopy. If we want the entire picture, we should probably call it integral field spectroscopy because not creative. The only way to do it. So if you are trying to get the picture of a whole galaxy, we're still going to use telescopes because they're the best thing out there. But instead of sending it to a normal mirror after the telescope has focused the light, we're going to use a really specific different mirror. It's not just a flat mirror, it's actually been broken into slices or strips. And each of the strips is slightly tilted with respect to the strip next to it, to the extent that it's sending the light to different places. What I mean is, the top strip of this galaxy is going over to the left, the central part's headed towards the middle, and the bottom slice is headed over to the right. So we just effectively took the galaxy, sliced it into pieces, and then just moved them away from each other. Because if they're next to each other and we disperse them, it's a disaster. We went over that. Everything is lost. But since we've already focused the light, it started diverging again, like it does when I'm not wearing my glasses or they're in the wrong place on my nose. So you need new lenses or something to re-image the light, and that causes it to form basically strips like originally formed on this mirror, but reformatted. So it's one new long slit. And we just went over long slits. We know how to do long slits. We already are really good at dispersing long slits. So we just took this image and we chopped it up and reformatted it to make a long slit that will then let us see the whole picture of the galaxy. Because we took that slit and we sent it to a spectrograph where it will be dispersed. So, you can actually see the little bits of galaxy in these pictures. And then it's spread out, and then you really have a mess because you just chopped the light into little pieces, spread it out, and put it on a detector. And then your astronomers are really sad because you just gave them a mess. So we also don't just get to build them an instrument, we get to build them software that will help them reassemble that data into a data cube. And I'll call it a cube because, the long slit was giving us just spatial information and wavelength information. So now we don't just have one spatial direction, we have both. So we're basically getting images at every wavelength, and we stack them up to get a cube. If you wanted, you could show this in the same way as a movie, with you having two spatial directions, and then instead of wavelength, you'd have time. So you can scroll through the wavelength or time direction and pause on a frame and have all the information you wanted to look at one individual emission or absorption line. That's really cool. So we have to build them software as well as instruments. They're very greedy. How rude. So that's all of integral field spectroscopy. I'm actually specifically building this part right here. But first, I should actually place it in perspective. So first we need a telescope. So at Carnegie observatories, we have Las Campanas Observatory. It's down in La Serena, Chile, along the South American coast right there. So I get to fly there, probably 3 or 4 times a year to try to do our observations, and I'll get to fly there even more, which is both good and terrible, to commission this instrument. My cat will be grumpy, because I'll be leaving a lot. But, oh well, we don't have a choice. But so specifically in Las Campanas Observatory, we have 4 telescopes. We've got 2 smaller telescopes over here, and then the Magellan telescopes, which are basically twin telescopes, I would say. They are called the clay and the body, and they sit next to each other, but they're not in the same building. They have separate domes that are connected by a catwalk, so you can just walk along it if you really wanted to at night, to admire the night sky. So zooming in specifically, I'm using the body telescope, and so that's 6.5 meters, or more usefully, 21 feet in diameter. And so we always talk about telescopes because we want as many photons as possible, as you called them, a light bucket. We want our bucket to be as big as possible, the primary mirror. So we always tell our telescopes apart by saying, this one's a 21-foot diameter primary mirror telescope, because that's one of the most important parts about it. Then you have to talk about the instruments, because that's really important too. But specifically, this site, this observatory is located in one of the best sites I've ever seen. So during my last observing run on the Bode telescope, this is what the sky looked like. So that's the Milky Way, in case it wasn't clear. That's one of the Magellanic Clouds rotating through. I think it's the large one. And then this happens And it's not actually the sun coming up, it's the moon. So even with so that's how dark the site is. Like, the moon casts shadows that you can see. So it's really incredible. So anyway, so this was my last observing run, and it was awesome. So this is a fantastic site and a fantastic telescope to put our instrument on. So then the other side is, I'm not building the spectrograph. Just not gonna knock the mug over. So I'm using an instrument that already exists. It is a wide field imaging spectrograph called IMACS. It has an acronym, no one cares. But what's cool is it's got a slot here. You can see how the panels come off. It's got a slot somewhere around on the other side, I couldn't get a picture of it, that you can take these panels off and you can put in something to modify the instrument. And that's really cool. So it's getting the light from the telescope like through this giant hatch where it attaches to that hatch. So the light from the telescope's headed inwards, and then there's a spot that we can modify the beam. So this is perfect because that means I don't have to build everything related to the detector or the camera. I don't have to touch that. I also don't have to touch the dispersion gratings or grisms or prisms because those are expensive and really complicated, and if someone already built them well, why not make something to just insert in to give this instrument a whole new capability that it wouldn't have been able to do before? So, okay, cool, perfect. So I don't have to build the spectrograph, bonus. What I do need to build is all of this in here. Excellent, so let's focus on that. So we were talking about integral field spectroscopy. If you're just putting in a unit to a spectrograph, that means we're building an integral field unit to modify an existing spectrograph. And it has a ridiculous acronym. It's called the Reformatting Optically Sensitive IMACS Enhancing Integral Field Unit. And we really did that to make it called the Rosie IFU. And in case you didn't catch it, I'm Dr. Rosalie McGurk. So that wasn't at all on purpose. But of course, the only logo we could use is a multicolored rose. That's just obvious. Anyway, so what exactly does my instrument do? So the telescope has given us an image that is not quite the field of the whole moon. So we actually need to stop it down a little to show you what I'm talking about. And inside of that, so this is what the instrument takes in, but that would be huge. Inside of that, we're actually going to grab a field that is 30 times smaller than the moon in diameter. And that is perfect because it is the size of our local galaxies. And I have to state for the record, since I'm comparing it to the moon, it sounds like I'm grabbing a small field. There is one other instrument that grabs a field this large in existence. So that's really cool. And they had to build a $100 million project to do it. And we're going to be much, much, much less in budget than them. So this is a much better idea, much more reasonable. Much. They had to build 24 spectrographs, and we're using one that already exists. Oh, God. So we're taking that image that's focused by the telescope, and then we chop it into 4 pieces immediately. No dilly-dallying around. It's the first optic the light hits. And I'm going to pick one of them to talk about it, but keep in mind we do all of the following to the whole field. So we take that one field, and then we magnify it by a factor of 3, so it just got huge. And then we chop it into 21 pieces. Okay, good. Then we take all 21 of those pieces. We need to demagnify them by that same factor of 3, because we need to bring the image back to the original size, because normally the spectrograph just works with a telescope. There's nothing in between. So if you magnified it, now you need to bring it back down so the spectrograph can handle it. So we broke it into all those pieces. If we dispersed it just like that, that'd be terrible. They'd all be on top of each other. There would have been no point. So now we need to line them up into a long slit. That's far too long to show on the projector, of course. So there are 9 more up there and 9 more down there to bring it up to the 21. Good, not complicated at all. So really, that was a cartoon version of what we're doing to the light. This is what we're actually doing with the optics. So we take the light from the telescope. It's focused onto this mirror where we chop it into 4 pieces. I'm only showing one to start because it doesn't need to be more complicated. Then we have a lens that magnifies the light. We send it to the image slicer, and of course, I can only show one of them because the image slicer slices the light and fans them out this way, out of the screen, or into the screen because it does it evenly on both sides. So I'm only showing the center one because we don't have 3D projection technology yet. We're working on it. So it's fanned out. We send it then to a second lens where it's demagnified by that factor of 3. And then a pair of just flat fold mirrors aligns the light into that slit to send it into the spectrograph. And so this is one of those fields and one of those slices that we made. This is all 4 subfields. So we chopped the light into 4 pieces, and then we had an image slicer for each of them. So that means we took the 4 fields and we chopped each of them into 21 pieces. So we have 84 optical paths. Great. And so we have to reformat each of those subfields into one long slit. So, and even more fun, I didn't mention it, when you're making telescopes, you either get to have a nice flat focal plane where you'd want to put a detector, but your image quality is less good to have it be flat, or you can have fantastic image quality, but the focal plane is curved, meaning the light is in focus there, or there, or there. So if you were putting it straight onto a detector, you'd be pretty bummed about that, because it'd be out of focus in spots. Ugh. But we don't have to do it quite yet. So we sliced all the light up, and we made it very complicated. Yay. So we sliced those 4 subfields up, we broke them into pieces, and we reformatted each of them into one long slit. So that means in our field of view, we have 4 long slits. And that's the size of the original image. So we chopped it nice and fine. Good. And so what I want you to note is the diameter of this is actually 2.5 meters, meaning, step outside the podium, it's about this big. Projector's bigger than my instrument will be. Great. It's very small. 84 optical beams, nice and compact, and very challenging to put together in a line. Great. So this is what that whole field looks like if you project it onto the camera or the detector that's busy reading the light out. And I'm going to get rid of the IMACS field of view because it's just messy. So when you disperse each of these, it's going to look like that. So that's what the dispersed light will look like from each slit onto our detector. So this is why it's really critical to have software to put it back together, because the astronomers would be very angry if you just sent them this. Check. Can't argue. So we're working on the software is what this slide is meant to remind me to say. Software in progress using Python. So then what are the other parts of building this instrument? Because I've given an overview, but what's actually happening? So I can talk about the image slicer. So this is what one of our image slicers look like. And to give it a little sense of scale, that's a calculator. So it's not large, not large at all. And so you can see each of the shiny slices here is slightly offset in angle from the one next to it. So that causes the image to be redirected, with the center slice slanting it straight back out. The other way to put it in scale is that's a dime. Oh, good. But to see what the image slicer is actually doing, since I haven't really, other than waving my hands wildly, I haven't shown you. So I'm going to give you a top view of this. So there it is. There's the image slicer, and it fans the light out into 21 beams. I'll say up and down, because that's what it looks like right now. But so that's the second lens there that demagnifies the light. There's one of the fold mirrors, and the other one's sort of a mess down that strip. And again, this picture is bigger than all of our optics. Our optics are actually much more like, the lens is maybe the size of my thumbnail. And the mirrors are probably more like the pinky nail. So yay, small, compact. So just to zoom in a little, I've actually deceived you. We didn't make it into one long slit. We actually realized that if you take a big circular piece of metal and you slice 4 lines down it, the structural integrity of that piece of metal is like shot. It's done. It wobbles when you poke it. So that doesn't work. So we realized that we can take each one of the little slices that we made, that we fanned out, and we can just offset them a little bit from the center. And so that's what this is really trying to show. That's one of the slices. My hand's bouncing too much. Good. So each of the slices are offset by 6 millimeters from each other, just so that the metal plate that we're building on top of doesn't give way to gravity, because of course this whole instrument has to spin. That'd be too easy any other way. It has to rotate with the night sky. Good, not complicated at all. So then, jumping to talking about the other part I can easily share is all of these optics are floating in space. That's not realistic. Clearly they have to be held by something. So I've been working with a mechanical engineer who is busy designing how to hold the optics I put in a box there. So we've got that second lens that demagnifies the light held by this great pink arm. We've got one of the fold mirrors words right there, and then another of the fold mirrors right there in red, and it sends it down through a little window into the spectrograph. Of course, they all have to be held by a clamp of some kind. We'll be gluing these in because it turns out you can't hold the other side of the lens without blocking the beam that's headed into the rest of the instrument. So it ends up being wonderfully complicated. And so we were trying to find out if we could 3D print this or if we could not 3D print it. And the answer is we cannot. Our 3D printer is not high enough resolution, but it's a really great test case. So I should have flipped the image, I forgot. That's where the lenses will sit. And we're doing them in units of 5, because otherwise, if you try to string all 21 together, it turns into a nightmare. It's already a little of a nightmare, but it would be more of a nightmare. So the light would be coming in from this side, it'd go through the lens, hit the fold mirrors, and then go down. Okay, so that's what my instrument will look like. It will be fantastic. We'll get spectroscopy over this whole area once we put everything back together. What science can we do with it? I'll go through it briefly since I did want to leave time for questions. So with this galaxy, it is a mess. It's what we call a polar disk galaxy, and who knows what is happening to this galaxy. Is the disk rotating? What's going on? It's a complicated picture, so we need a much more complicated way to look at it than just a long slit. So if we can actually make it to the movie. So this galaxy shows rotation, and it has emission in nitrogen. Is it going? Yes, it's going in nitrogen, hydrogen, and sulfur. So it's going to slowly move through it, and there it goes. That was one of them. So we just saw a flash of nitrogen, hydrogen, and nitrogen again, and those were 2 sulfur lines. So what way is it rotating? We'll do it again. Blinked, okay. It's really rotating from left to right. So even though it's got this ridiculous feature of a really weird sort of bulge or something that's happened, hasn't affected the galaxy. The galaxy might be star forming a little more because of it's probably a merger going on right there, but it hasn't affected the rest of the galaxy. It's rotating as normal. Okay, good. We wouldn't have known that without a much more complicated picture. It could have had plumes. It could have had all sorts of weird things. So here's another example of how awesome it is to have the whole picture. So this is a galaxy. Start over. This is a combined image of Hubble and the Chandra X-ray telescope. So the X-ray telescope's shown in blue. And specifically, we're looking at a disk galaxy that's falling into a giant galaxy cluster. So it's falling into a whole bunch of hot gas, and it's going to interact with tons of other stars. But while it's interacting with this hot gas as it falls into the galaxy cluster, that hot gas is actually stripping gas that was originally part of the galaxy off of it, leaving this phenomenal hot gas plume that you can only see in X-rays and in emission lines. And what's really fantastic, if it will do it, you can see the hydrogen and nitrogen lines of this gas even extending out to this, 100,000 light years. And it's not just streaming off the galaxy, it actually still knows about the rotation of its original galaxy. Because you can see the gas on there is rotating as it's streaming, there it goes. So it's rotating as it's streaming off the galaxy. We would never have guessed that. We would have guessed that once it was stripped from the galaxy, it wouldn't know where it came from. It wouldn't retain any of that rotation. So then this is the final one. There's an active black hole sitting in the center of this, and it's busy blowing filaments of gas out into sort of these cavities, these big radio bubbles, and then it's slowly starting to cool. But the system is horribly complicated because it's not just blowing them in one plane, it's blowing them in all of it. So if you want to try to understand what's happening, you need a much more dynamic approach to studying it. So it should zoom through the boring wavelengths until it reaches the emission lines. But once it does that, you can start to see there's ridiculous, incredible, far-flung structure even out up to there. And there's even a high velocity thing right close to the galaxy, meaning that the black hole has recently blown out very fast-moving material. And then it's also got some sulfur emission, even at sort of close, but sort of at close radii from the galaxy. So by studying something like this, you might be able to piece together how many epochs of the black hole blowing giant bubbles have happened, how far they can travel, what speeds they might have started at to get to at that distance. So you can actually start to piece together how black hole feedback works, because we don't understand how black holes blow bubbles like this. We don't know how often they do it. We don't know with what energy they do it. So you really need data like this to try to build it together, try to put it together. And then finally, movies are beautiful, but they're very hard to publish, at least on a paper that other people might read, weirdly. So actually what astronomers study is often plots much more like this. So this is the pretty standard disk galaxy, and they've shown where they got data enough to measure the velocity of the gas in this galaxy. And so I meant to put velocity up here, but I forgot. So this is the velocity that they measured using the Doppler shift of this gas, with more blue gas being blue shifted towards us, and red gas being red shifted away from us, because we're not creative again. So you can see, not only is the galaxy rotating, but it has really detailed structure as it passes through the center. So you can use 3D data like this to complexly model the galaxy as not just, one line, but as an actual 3D structure to try to understand dynamically where is the mass in the galaxy. And if you have really high resolution information in the center, you can measure the black hole mass that way by watching how it's tweaking the gas around it. So that's really fantastic. So this is more of what data looks like when we talk about data, not just beautiful movies. So then in summary, I've shown that spectroscopy of emission and absorption lines shows the presence of elements and their movements through the Doppler shift. Long-slit spectroscopy only shows part of the picture, while integral field spectroscopy shows the entire picture. And our integral field spectrograph will open up a whole new avenue of science that can be done on our Magellan telescope. So with that, thank you so much for your attention. I can take questions about all the things. And you're also free to escape if you need to, because it is the evening. And I'm happy to answer questions about career stuff, like how I got here and why I chose this. And so if you want, you can go over to the microphones, which you're supposed to press the little power button on, and it might turn on. If you have any questions.
Yeah, thank you so very much. That was wonderful and truly awesome work you were doing.
Thank you.
And I'm stealing some of your ideas from your slides from my own classes.
Yes.
If you're interested in asking some questions, please do line up at the microphones.
Or you can just run away. That's okay too. Or I can take questions afterwards if no one wants to ask in the big hall. That's also okay.
Well, if I could ask one to get started, the mirror that you make that breaks the light up into 21 slits, that is a really delicate piece of optics.
Yes.
How did you build that?
Great question. We're actually working with a company that, when we talk about machining things, we often just talk about metal. So that's when you talk about machining things, people imagine you're working with metal. We, of course, are working with glass. And we are working with very fine glass. So it takes very custom machines. The glass actually has to be immersed in water so that it doesn't overheat and shatter and chip and be a disaster. So we will be probably taking slices of glass that have already been made for semiconductors, for example, and we'll be able to cut out specifically pieces. And I even, come on, I know you used to go. No? You don't want to? Great, perfect. So the way we do it is we actually are cutting slices out of the substrate, and we'll cut 4 holes. We'll say 2 of them are in red, they're fixed in each slice, and the other 2 are slightly moved in position so to make the top surface is what we actually care about here. This bit of the mirror is the actual part we care about. The rest of this is, just the substrate below the shiny part. So these holes will allow each of the slices to rotate. And what I really mean is these would be the fixed holes, and these are the rotated holes. So we have to make the mirror shiny and give it a finish and polish it to a shape. And then when we pull that dowel pin out, we can put the dowel pin through the other pair of holes. So those are the fixed holes, and these are the rotated holes, so that it moves each of them to a different angle. So it's horribly complicated because I didn't say it, but each of these are 0.6 millimeters thick. That's why we needed to magnify the light with a lens, because otherwise it would have been 0.2 millimeters, and that would have been pretty impossible to machine. But 6 millimeters is just large enough that we can handle it. We won't break our substrates as we build them.
So that's a mock-up?
Yeah, this is a mock-up made out of metal. We are making one with a company right now. So we've actually built up all of our mechanical drawings and we've sent it to them, and they are going to machine it.
It's going to be glass.
Yep.
Okay, thank you.
So in astronomy class, we learned that when speaking about telescopes, the bigger the better. Do you think that like if you were to make a bigger type of your telescope, you would get better data?
That's a really good question. So we always want more photons. So we always want bigger telescopes because if you have more photons, it lets you reach things that are fainter intrinsically that you wouldn't have seen with a smaller telescope. And so since that I moved back automatically while I was talking about it, because the further something is away, the fainter it is as well, based on the R² physics law. So that means that with a larger telescope, you can get to see fainter, further things, but it's really challenging to build bigger and bigger telescopes. So Carnegie Observatories is actually involved in building what is called the Giant Magellan Telescope. And so our Magellan telescope is 21 feet. This one is 3 times larger. So it's 63, I'll just say. I can't multiply it in my head. 63 feet, that's too many people. 21 was like 4 of me lying down. That's very large. So it's like the size of the room, right? That's too much. So that's really hard to get the image quality to be as beautiful as you want it. Still totally possible with a lot of very technical engineering. So, and it's also going to, it's one of 3 of these giant telescopes that are being built. And that means that if 3 telescopes have to feed all of the world's astronomers, the telescope time is going to be more competitive than anything. So we already have to write proposals to get telescope time. The telescope time on these large telescopes, even our 21-foot, is competitive enough that you have to write it down on 6 pages and submit it to a committee to say, really, you should give me the time. Don't give my friends the time. Me, I want it. So then you can imagine if you have 3 telescopes to feed all of the world's astronomers, it is going to be a very competitive discussion about how to allocate telescope time. So I would not say the giant ones are going to be the most amazing, the best. I mean, they're going to let us do science that we can't do on some of the smaller telescopes because they can collect more photons and see further. But there's definitely, we will still be using all of our smaller telescopes because you cannot feed all of astronomy with 3 giant telescopes. So that's a great question. Yeah?
So in a similar vein, this is obviously superior to the current method that we have. So do you envision that it's going to be a retrofit that all telescopes get and that you'll be doing a spacewalk to Hubble to put it on that one too, and et cetera, et cetera?
Oh, I would like that a lot. That's a fantastic question. So it depends if the instrument that you would want to retrofit has a nice spot where you can insert an instrument. Not all spectrographs have that capability. Some of them just have a wheel that puts a long slit or like a different diameter long slit. Like it has a set of long slits to put in. And so if your instrument is not meant to have this space where you could input a modifier like this, that would be out of luck. But there are a bunch of instruments that have a field like this, so if we can prove we can do it here, we will be doing it on other telescopes. I'll be employed.
Your postdoc will admit something.
Yes, exactly. Yeah.
So I kind of have a naive question. I don't know how we used to look for signs of life in the deep space. Do you think using the integral spectroscopy feels that the thing you develop, there will be an easier time looking for signs of water in the deep space? Is there a possibility?
Oh, that's a really good question. So if you're looking for signs of life in deep space, the integral field spectrograph is probably not the right answer
But looking
for
for
it.
water, like
Yeah. If you're trying to look for water, well, so the challenge is you took all the light that you might have concentrated just in one long slit, and you added all these extra optics in the way. And so every time you hit another mirror, you decrease the amount of light by, a couple %. And so by bouncing it off all of the extra mirrors in my instrument, you just decreased what I'll call the throughput, the amount of light that makes it through,
So you have to
by
have a
some
lot.
amount. Better than a lot of other ways that we try to look at large fields like this, but still not as good as just focusing on one slice of the galaxy and just taking it straight. So if you're trying to detect water, that might mean there was other life out there. I would probably stick to using long-slit spectroscopy for that reason. Good question. Anybody else? I like answering questions. Would you mind walking to a microphone so people can hear you, or?
I'm kind of hemmed in. I'll just talk.
Okay, loud.
Help me out with the blue shift, red shift. The speed of light is constant. So how do we get it to blue shift and red shift?
Good question, good question. Ooh, going. No, you don't want to go? Come on, thing. Why? Don't be a jerk. So when we're looking out in space, things are moving at different speeds. So this is an example of just one object that is moving and rotating just on its own. So with respect to the center, the galaxy is moving. But actually, all of space is expanding away from us. Okay, that was a statement right there. Just taking that as a statement, that means that things that are, and the acceleration and the space is expanding in an increasing way. So that means that the things that are closer to us are moving at one velocity, the things further away are moving at a higher velocity, an even higher velocity, and so we actually see the light from each of those galaxies at an increasing velocity and therefore at an increasing redshift moving away from us. So that lets us actually use that velocity as a proxy for distance, but it shows up as galaxies that are further from us are more redshifted away. So if you're trying to look at one hydrogen line across the whole universe, you cannot look at the hydrogen line where it would be in the sun. You have to keep looking to redder and redder wavelengths to chase it as those galaxies are moving further and further away. So that's how galaxies are redshifted. Just sitting within our own galaxy, we've got stars that are moving towards us and stars that are moving away from us. So some of those stars are blue shifted if they're moving towards us, and some of them are red shifted. Yeah?
What I need to say is the speed of light is 300,000 kilometers per second.
Yep.
And that's constant. How do we get the speed up?
So the light is not going any faster or slower. Instead, it is changing in wavelength. So if you remember the equation that I'm sorry to bring out because equations make people sleep, energy is proportional to the frequency. So that means that if the light is moving faster and faster, well, not faster, wrong word, bleh. It's not actually that the light is moving at a different speed, it's that space is expanding underneath it. So the space expanded, so it's now moving in a different color. Still the same energy, well, messy. You spread it out more. Awkward. Good question. Yeah.
Hi. Excellent work, really working on difficult mechanical stuff as well.
Yep.
So you've been focusing on examining galactic structure, the majority
It's an easy
of.
example. Yeah.
Yes. So have you looked into, for example, other structures like protoplanetary disks, things like this? Can you apply the same technology and gain some information, valuable
It's a
information
great
out of that
question. So the challenge with if you wanted to look at a disk that was busy forming stars or busy forming some type of planet around a star, so as you said, either way, the problem is they're very small structures. Unfortunately, far smaller than a galaxy, so therefore, if my field of view very nicely fits one of our local galaxies, very small in the field of view.
So there's resolution limits.
So there's resolution limits to what we can do. So ideally, I would slice my image as many times into very skinny pieces, as many skinny pieces as I could, but then you wouldn't be able to see things that were above a certain brightness. Things would be so faint that you would have chopped them up so much that you won't get any light. And you would have probably have to build a new spectrograph because you chopped them into so many pieces and had to make so many more long slits that it very abruptly got complicated. So the one comparable instrument in the field, which is built by the European Space Agency, so they actually chop their pieces of their galaxy up into 3 times smaller pieces. And because of that, they have to build 24 spectrographs. They also can make out finer wavelength resolutions than we can by a factor of a couple. So then you just spend 1,000 orders of magnitude on the price. So we made a choice about what spatial resolution and spectral resolution we actually wanted to see. Great question. Yeah.
Hi. I'm wondering if, because beyond the absorption and emission spectra, can you take this design and apply it and sort of build it differently, or is it the same to get other types of information on different types of light? Could you take that design and then make something that could, reveal gamma rays, for example?
Ooh, that's a really good question. So she's asking not just, so my instrument specifically looks at the optical wavelengths, so the lights that we can see. If you look beyond it, you can see into the infrared, or you can see into the ultraviolet, or even further to higher energies. And the challenge with everything in higher energies is the light is so high energy that it actually doesn't bounce the way we want it to. It likes to pass through the mirrors instead of bouncing off them. So for example, the X-ray telescope, Chandra, they don't actually make a mirror that, the light coming in bounces off and goes to optics. They actually make mirrors that the light bounces off of it, grazes off of it, and focuses it. So this would be very hard to do. It's a really fun idea, though. Don't know how you would do that. I really like the idea, though. But mostly, the other life challenge is most of our higher energy instruments have to be in space.
Right.
So if we could just launch them all.
Yes.
I love that idea. I'm going to think about it. Thank you. Anybody else? Yeah.
I'm Jude, and I teach here, so welcome to our campus. We're always looking to encourage more women in STEM.
Yeah.
Can you tell us about your path and how we could encourage more women?
Ooh, that's a great question. So my path was, I really liked science and engineering. I took a lot of things apart as a child, didn't always put them back together. Different problem for my parents. But eventually, I decided I liked astronomy the most because my mom sent me to a stay-away camp that I didn't want to go to at an observatory. I was against the whole idea. And while I was there, they spent a week teaching about astronomy, and then they made the phenomenal mistake of letting me drive with a hand paddle a 26-meter radio telescope. So that's like a giant radio dish with a hand paddle. It's the best thing. They also let me do a research project, so I could actually imagine what being an astronomer looked like by doing a little bit of research. So if you're trying to decide what field you want to do, see if you can join anyone doing it, because what you learn in class sometimes looks like what you end up doing as a job, and sometimes it doesn't at all. Sometimes quite a lot it doesn't at all. So seeing and actually doing a research project really helped me. But even more so, it revealed that the community of people who taught astronomy, who did astronomy, were a community of people I wanted to join. Because if you go to physics, unfortunately, there are 10 or 15 or 20% women, and then you walk into the astronomy part of the University of Washington, and it's 50%. And as you go up higher, there aren't as many women, but there's still a much higher fraction than among the physicists. And that is not to say we should not change physics. We absolutely should. But in terms of finding a community where I felt like I fit, that was huge, because there were just lots of people like me. And that matches the white skin part. We are working on actually fixing diversity in other axes. For example, last month's speaker was Alex, and he's Asian. So that's a good start. But no, so we actually, at Carnegie, we have people of all different skin colors, and actually we also have international people of all different skin colors. So that's really fantastic, because you learn the most when you're among a diverse group. So that's my hand-wavy version. It's also overcoming, when something doesn't go the way you want. Either you work harder, or you work with friends, or you actually weirdly talk to your professor, or you crazy things like that. But if things aren't working, making sure you are courageous and strong enough to ask for help. It doesn't fix everything, but if you have a community who you can talk to, even those scary or not so scary professors, they actually would really like to help. So do ask, because we can't help you if you don't ask. Anybody else? No? No?
Thank you so very much. And
Thanks,
thank you everyone for coming by. Again, the next talk will be November 20th, same time, same place. I hope you come for that as well.
Allison's an awesome speaker, I promise. And the DNA of Galaxies are excellent.